Yes. Hi, good evening,
Hi,
everyone.
hi, good evening. Can
Am
you
I
share?
audible?
Yes, we can hear you. So so just to confirm, you're fine with your talk being recorded?
Yeah, sure. It's okay. It's perfectly fine from my side. Okay, so I try to share my screens without just wasting much time.
Ja, det er Morten. Ja. Jeg var optaget. Du har ringet til mig.
I think he
Nej,
need
ikke længere. Det gjorde du før, men ikke nu.
to mute his microphone.
Ja.
Everyone, now you unmute and speak. Sorry. So, Vikas and Sanghasri, you both have to unmute. You are muted. I muted everyone so that.
Okay. Yes.
Okay, I got it.
Okay, so our next speaker is Dr. Sanghasri Mukhopadhyay. She's currently an assistant professor at the Vellore Institute of Technology, and she completed her PhD in energy and process engineering from the University Savoy Mont Blanc and the University of Grenoble in France in November 2020. And she was a postdoc as a regular researcher in CNRS, also in France. And after that, she has been an assistant professor at VIT. Her research interests are in hydrodynamics and instabilities in thin films. Today, she will be talking about thin films on structured packing. So over to you.
Thank you very much for such a nice introduction. And again, good afternoon to everyone. So today I will be talking about part of that I have done during my PhD. So this is the basic work, which is a thin film on structured packing. So first of all, let us understand, I'm not sure if my entire screen is visible to everyone. Can you please confirm, or maybe I will...
Maybe could you like make it full screen? We can see the window.
Okay, let us try to do that. Maybe.
Okay, yeah, now it's good.
It's better. Yes, it's better.
Yeah, thank you.
Okay, so first of all, let us understand that about a bit about the structure packing and why we need, and why, because as I always tell to everyone that before you are doing any research or even any activities in your life, you should be able to answer yourself that why you are doing that. So as the problem comes from the falling film hydrodynamic and wave nature in the structure packing, so it is better to understand a little about the structure packing and where we use it and why it is so useful. So basically structure packing or gauge packing we use in the chemical industries, like for heat exchangers or condensers or evaporators, this kind of stuffs, where we need a large surface area, a large contact area between the different fluid things like gaseous phase or liquid phase or two liquid phase, this kind of stuff where we need. So in that cases, because structured packing has a porous property and it has a very complex structure, so it drags the fluid from one place to the another place and spread the fluid over the surface area, so that it can create a large contact area between the fluids. So there are different kind of structured packing that is used for different purposes. For example, gauge structure packing, perforated packing. So their use are in the different. So sometimes they give more exchange of mass. Sometimes it's for more exchange of heat. For us, we focused on the gauge structure packing. So in that cases, we have some wear gauge structure packing. So it is maybe nylon wear, metallic wear, or woolen wear. So after that, they are woven into give you a thin sheets of the packing, and then they are corrugated, give it a particular shape of the packing one after another, and to make it as per our need. So okay, I'm very not much expert about this structure packing itself, but mostly these structure packings, they are used in these flavor factories and vacuum distillation, and that I told you, the places where we need to reduce the pressure drop, because of course in an experiment or in an industrial work, we don't need the pressure to be dropped from one point to the another point. So the complex structure of these packings assure us that they reduce the pressure drop, and they have promote the spreading because of their porous nature or because of their actual orientation. And also they give the large surface area that I already mentioned, and also they reduce the possibility of the flooding because of their porous nature. So these are the main advantages we get with the structure packing, and that's why we are more interested to see that how the different sorry. Sorry, something technical happened, problem. So this structure packing, we wanted to see that how if thin film flows over a structure packing, how the hydrodynamics property of the thin film changes with respect to the packing, the presence of the packing. So there are a lot of aspects to see this problem. First of all, we can check with the porous property of the packing itself. So that's what the first work we have done is. The one is called thin film on anisotropic porous medium. Why it is we have taken anisotropic? Because of the orientation of the packing structures, the permeability differs from one direction to the another direction. That's why we call this porous medium as the anisotropic porous medium. And this is actually the diagrammatic picture of the problem itself. So as you can see that we have an inclined porous medium which is bounded by a rigid wall in the one side. That's why we called this problem as the one-sided problem. And this is saturated by the film that is flowing over the porous medium. So same film that saturates the porous medium. And this porous medium is anisotropic, so the permeability from the one direction to the another direction is different to each other. And it's of course a free surface flow, so thin film is flowing. And we have taken the thickness of the porous medium to be as a small d, and capital H is the entire thickness of the continuum, which includes the thickness of the porous medium and the thickness of the liquid film that is flowing over it. And also we have taken the porosity of the medium to be constant. So the void fraction, that means the ratio between the vacuum and the solid part of the matrix, is constant everywhere in the porous medium. But the permeability changes. That means the orientation of the voids is changing from one side to the another side. So this is basically the diagrammatic picture of the problem. So here, one thing I must say that we have chosen approach which is called one domain approach. Normally when we study the porous medium and the thin film things, we take the porous medium and we use that Darcy-Brinkman, or maybe sometime with the Fukushima equations or Fukushima's law. And for the liquid layer, we use the Navier-Stokes equation. And between the porous and the liquid layer, what we do, we have a set of boundary conditions to adjust between the interface of the porous and the liquid layer. But in that case, so we need to handle some extra set of boundary conditions. So we have boundary condition at the bottom of the porous layer, we have boundary condition at the free surface, and also a set of extra boundary conditions that we need to handle, which is in the porous and the liquid region, intermediate region. But one domain approach is an approach where we consider the porous medium as a pseudo-liquid layer, and we assume that the characteristic property of the porous medium, for example, porosity and the permeability, they have a continuous variation from the porous to the liquid layer. And there is a small transitional zone, we call it, there is a capital delta here. In that transitional zone, actually, the variation of the porosity and the permeability effectively changes from the porous to the liquid layer. So this is the approach was invented actually by some French researcher. And later on in Paris, the group is working on this particular approach, and they call this as a one domain approach. So there are lot of evidence of working in this approach even before us also. So we adopted this approach because we thought that there is no need to handle the extra set of boundary condition, because the modified Navier-Stokes equation is applicable in the porous and the liquid layer both. So we have the set of boundary condition at the bottom of the porous layer. For our case, we have bounded it by the rigid wall, so there should be no slip boundary condition and the no penetration boundary condition. And in the free surface, the usual boundary condition that we use, like valence kinematic boundary condition, stress valences boundary condition, at the free surface we can use it. So this is actually the set of modified Navier-Stokes equation that I was talking about, which can be applicable in the porous and the liquid layer both. So we have the mass balance equations here, and we have the modified momentum balance equation, which includes the Darcy term, and which includes the Brinkman term and the Darcy term at both. So this is the set, and for our cases, because I told you that we have an isotropic porous medium, that means the permeability changes from one direction to the another direction. Basically, permeability is a tensorial quantity, but for the simplicity, for our simplicity, we have taken, because we are in the two-dimensional case, so this vector we have defined in this way, that it has a part that is changing in the streamwise direction. We called it kappa x, which is a function of the cross-stream permeability. Of course, this porosity and the permeability both are the functions of the functions of the cross-stream direction, because I told you that the effective properties of the porous medium changes from the porous to the liquid layer, so it must be the functions of the cross-stream direction. So in that cases, we have taken the permeability in the two different directions, which is the streamwise direction, we called it kappa x, and in the cross-stream direction, we called it kappa y, but both of them are functions of the cross-stream directions itself. And our fluid is driven by the gravity itself, so that's why we have the terms including the gravitational force also. So some important parameters that I told you about the definition of the permeability and the porosity. So let us understand it using this pictorial representation itself. So here I have the cross-stream directions, which I call y, and I plotted it the permeability as a porosity, which is epsilon, as a function of the y. So our thickness of the porous medium, the dimensionless thickness, we have taken to 0.5. So from 0 to 0.5, when we are inside the porous medium, we have a constant value of the porosity, which we have fixed here at 0.78. Then in the liquid layer, from 0.5 to the above layer, we know that the liquid has a permeability. We know that the liquid has a porosity, which is 1. So the value of the porosity is 1. And in between this layer, I told you that we have a small transitional regime. So we have kept the transitional regime to be very smaller value so that it will not affect in the actual flow conditions. So we have kept the transitional regime to 0.001, and we have defined the permeable porosity using a Heaviside function, which has the two characteristics, like inside the porous medium we have a constant value, and inside the liquid layer we have a porosity which is 1. So we can simply define it in this way, the porosity as a function of the cross-stream direction. Similarly, for the permeability, the x and the y direction, what we can do, we can have a mean value of the permeability, which is defined by the Darcy number. Mean permeability inside the porous medium, we have some sort of constant mean permeability, and in the liquid layer we have infinite permeability. So that's why we have plotted it as 1 by permeability, so that it comes to the value of 0 in the liquid layer. And using the same technique of defining a Heaviside function, we can simply define the permeability in this way. And this parameter, which we call zeta, is the ratio between the permeabilities of streamwise and the cross-stream direction. So this is the anisotropic parameter. We call this zeta as the anisotropic parameter. And from the definition itself, we can see when the value of the zeta is high, that means there is more permeable, the play matrix is more permeable in the cross-stream direction and less permeable in the, more permeable in the streamwise direction and less permeable in the cross-stream direction. So that means the interface between the porous and the liquid layer almost behaves like a rigid one because there's no much exchange of fluid between the porous and the liquid layer if we have higher anisotropic value. So about the base flow, this graph is quite important for us to understand that how this fluid is flowing inside the porous medium. So film of constant thickness, unperturbed film we have. So these solid lines are actually the solution of the base equations from the base flow itself. And in the porous layer, we can see that changing the mean permeability value, which is given by the Darcy number, we have different profile of the velocity. And for example, we talk about the Darcy number to 10 to the power minus 3, which is the red line. So we can see that it is a no slip condition is applicable at the bottom of the layer, and there is some sort of uniform flow or parallel flow inside the porous layer for some values, and then there is a change in the velocity, drastic change in the profile, and after that it resembles a little bit like the parabolic profile. So we have approximated this value. So it looks like if we have the no slip condition at this point, which is let's say the delta B, we can easily calculate this delta B by balancing the Darcy drag and viscous diffusion terms. So we will get some values of the delta B. So if we moved the no slip condition from 0 to this point delta B, so that means the effective no slip condition is at 1, the total height, minus delta, the thickness of the porous medium, plus delta B, which will give me this point particularly. So if we approximate this velocity profile using the profile of the no slip condition, which is the parabolic profile that we normally get from the no slip condition, so that approximate quite good in the liquid layer, and there is a deviation in the porous layer which is predictable, which we can expect because it is a no slip condition and it is the original solution from the porous layer itself. So that's how, if we consider this velocity profile, we have approximated it. So we can see that for the moderate value of the Darcy number, when we have like 10 to the minus 2 values, we short of a good approximation in the liquid layer. But when we have a bigger Darcy value, for example 0.1, that means the matrix almost looks like doesn't exist porous medium. So that's when it is hard to approximate. And it is easy to approximate when the mean Darcy value is much higher. That means the porous medium almost behave like a rigid medium. And also, seeing this picture itself, we can see that we have the 3 regions. We have 2 Brinkmann regions, so in the top of the bottom of the porous medium, and at the interface of the fluid and the porous layer, we have Brinkmann regions where we have the shear, which is effectively working in there. And in between these 2 Brinkmann sublayer, we have a Darcy region where we have a uniform flow we can expect. Okay, but we see that the base flow is independent of the anisotropic effect. So there is no anisotropic effect in the base flow. Whether we change the anisotropy to the lower value or the higher value, it will always be the same. So some sort of linear stability analysis we have done using the Orr-Sommerfeld technique, surface mode analysis. So again, we have seen that in the wave number and the Reynolds number plane, when we perform the marginal stability analysis, so the critical value of the Reynolds number for the instability, we can easily approximate it by this REC. REC came from that if we move the no slip condition from bottom to the top of the Brinkmann sublayer, which is 1 minus delta plus delta V, and we analyze the Orr-Sommerfeld, accounting the no slip condition at that point. So the critical value of the Reynolds number will be given by this Reynolds number, which is approximately same with the value of the critical Reynolds number that we get using the Navier-Stokes equation Navier-Stokes equation for the entire fluid porous system. Why? Because I told you that the effect of the anisotropy is not in the base flow itself. The effect of the anisotropy comes for the higher values of the wave number. So we have analyzed and we have seen that the anisotropy effect is coming at the second order of the k square of the, I mean, if k is my wave number, so it is coming the k square term. And also there is another important thing to notice here. So this left panel is for Darcy number, which is quite smaller, and right panel is for Darcy number 10 to the minus 2, which is quite bigger. So we said we can see that raising the anisotropic value is giving a dual effect depending on the mean value of the permeability of the matrix itself. So we can get a conclusion from the linear stability analysis itself because of this dual nature. It's very interesting to see. Also, this dual nature comes in the higher values of the Reynolds number. In the low value of the Reynolds number, there is not much effect of the anisotropy is visible. When we go for the high value of the Reynolds number, we can see the effects. Because for this, the mean permeability value, if it is small, that means the matrix itself resembles more or less less permeable medium, which is resembles somehow the rigid medium itself. So if you raise the anisotropic value, that means there is not much exchange of mass between the fluid and the porous layer. So that reduces the viscous damping effect, and that's why there's a high fluctuation, and that was the region actually. If we increase the anisotropic value, we will be able to see the instability or the unstable region increases in that cases. Similarly, if we, for the lower Darcy value, what happens, because if we keep increasing the Darcy number, we will be losing the amount of the Darcy region actually. If you see in the base profile itself, for example, 10 to the power minus 2, which is this blue line. So we see that the uniform flow region, that is the Darcy region, which is decreases if we keep increasing the mean permeability value. So it's the viscous, so the Brinkmann sublayers, the thickness of the Brinkmann sublayer increases if we increase the mean permeability value. So that's why it gives more stabilizing effect when we increase the anisotropy for the higher permeability value. So this is from the, and then what we done, we have modeled this phenomena using a lower dimensional model we call weighted residual. So this is a little bit of representation how we do. Normally we eliminate the pressure gradient, we make a boundary layer equation, and then we decompose the velocity into two parts, which is the base flow and the correction terms. And then using some algebra, we make this averaging thing with a proper appropriate weight, which is called W. That's why this method is called weighted residual. And we get a two-equation model based on this evolution equation of the flow rate, local flow rate Q, and the thickness of the continuum, which is capital H. So if this model looks like something like this, which is a little bit combustion model, because we have QL, which is the flow rate in the liquid region, and QP, which is the flow rate in the porous medium. And also this is exactly the structure of the model. I will not go into the very detailed discussion of this. If someone is interested, we can discuss later about it. So in this model, we have 54 coefficients, and we used some numerical techniques to get this model. Because it is not possible to work analytically with this model. So we can see that the anisotropy is coming into the picture using this viscous diffusion terms actually. There is no inertial term, there is no effect of the anisotropy. So we have, after getting the model itself, we compared the results from the linear stability analysis by Ward-Sommerfeld, that directly from the Navier-Stokes equation itself and from the model itself. So two-equation model is that if we consider the same flow rate in the liquid and the porous medium, so that is previous researchers have done this. So that's what we call it two-equation model. And the three-equation model is our model where we have decomposed the flow rate into the two region of porous and the liquid region. And the approximate model is the model where we have approximated the coefficient that we got from the three equation model using some algebraic approximation, using some polynomial approximation to be precise. So we have checked that this dotted red line is the Orr-Sommerfeld result that we got. So we have seen that the two equation model doesn't work well because they have considered the flow rate is the same in the porous and the liquid layer, which is not the case for higher values of the Darcy number. Higher values of the anisotropy as well, because if you have the higher values of the anisotropy, that means there is not much exchange of fluid between the liquid and the porous layer. So there is a problematic thing happens with the flow rate of the porous and the liquid layer. So precisely for higher values of anisotropy, the three equation and the three equation approximate model works much more better in these cases. So the same kind of things we can observe for the higher values of the anisotropy. So then we have moved to some time-dependent simulations. So we have periodic inlet forcing, and we have the open flow condition, which is a no flux condition. So we have done this simulation for Reynolds number to almost like 50. Resembles this data from experimental data by Liu and Gulu. So we have taken the same sort of inclination angle, frequency, and the viscosity, and the Kapitza number to check the value. Okay, the no slip model means that if we approximate the model using a effective no slip condition that I show, as I already showed you in the base profile. So if we approximate the base profile, if we approximate the model itself using taking the no slip condition at the bottom of the Brinkmann sublayer, so that will give you the no slip condition model. And another two models are for the entire model itself. I mean the exact model for us, which is for low value of Darcy number and higher value of Darcy number. So we can see that this QP, the red line, is basically the flow rate into the porous medium, So the flow rate in the porous medium is always less when you have the matrix, the porous medium, which behaves like almost a rigid wall. So that's why the mean permeability is less. Whereas we have an effective good amount of flow rate when the Darcy number is high. That means the fluid can flow inside the porous medium. And also, if we increase the anisotropy, that means we decreases the possibility of exchanging of fluid from the porous to the liquid layer, then the flow rate in the porous medium, which is the red line, almost becomes flat. And also because of this tension, because of this phenomena, increasing the anisotropy will decrease the thickness of the Darcy region. And we can see that the amplitude of the fluid, amplitude of the wave increases in the cases when we have the bigger anisotropic permeability relatively to the smaller anisotropic permeability. So there is a small conclusion about the time-dependent simulation that we have got. So that's why we can say that if we raise the anisotropy, we reduce the fluctuation of QP, which is the flow rate in the porous layer. And that's what we limit the mass exchange between the liquid and the porous interfaces. And so that will give you high film height fluctuation in the Darcy sublayer decreases, and this mechanism amplifies the capillary ripples for the low values of the Darcy number. Because if you see for the low values of the Darcy number, we increase the anisotropy value, which is 1000. We see the number of capillary ripples is more than the number of capillary ripples in the right side panel, which is for small mean permeability value. So this was the main outcomes that we got from the study, but there are a lot of things we have performed in this paper. So from my side, this is the thing that I have done. So if you have any questions, thank you very much.
Thank you very much, Sanghasri, for your nice presentation. So any questions from the audience, please go ahead.
Hi, Sanghasri.
Yes, hi.
It's a nice presentation.
Thank you.
I have one question. So, what are the boundary condition which you have considered here?
Yeah, okay.
I
So
just
if I
missed a few slides.
Yeah, sure, no issue. So because we are taking this one domain approach, so we have a bounded rigid wall at the bottom of the porous layer. So we will be considering the no slip boundary condition and the no penetration boundary condition at the bottom. And then at the interface, we will be using the usual boundary condition that we normally use, like balance of kinematic boundary conditions and then balance of the tangential and the shear stresses. So it's that's all. This is the set of boundary condition we have
So
used
here,
in the
so here
yes,
you are considering the inclination, this
yes,
theta.
yes.
So how it is like influencing the stability? How it is like
Actually, actually, it works in same way. It doesn't matter much with the porous medium. So if you increase the inclination, it will give you a more destabilizing effect. Like this, if I talk about the in the terms of the linear stability or something like that, so the critical Reynolds number value will be decreasing if we keep increasing the inclination angle. So there is not much thing to do with the porous medium or something like that, because inclination angle always has its own property to react with.
so have you done about the another boundary condition which is called two? Like in this you have considered some boundary condition. Another there are two types of boundary conditions while dealing with this kind of problems.
Which boundary condition are you talking about?
Like the here you are taking the one method, no?
Yes, yes, yes. You are,
Yeah,
yeah,
there is a
here we are actually we are taking this approach which we call one domain approach. So if you are talking about the two domain approach, I mean, if
yeah.
you are talking about including the more boundary condition in the fluid porous interface, yeah, we have I actually have done this. So we get some sort of similar results from there. So it's
It is similar. That's not like
at least up to the linear stability.
uh, okay. Thank you.
Any further questions from the audience?
Hi, I just
Hi.
had one question. Like,
Yes.
you are considering the viscosity of the liquid here, right?
Yes.
Okay, so is like, are you considering it as just as a Newtonian, or I kind of missed the first part of the presentation?
Yeah, yeah.
I'm
We
sorry for that.
right now we have used this Newtonian fluid only.
Okay, okay. So, have you done anything, something like a non-Newtonian also?
Not yet.
Okay, maybe there is time for one more short question. Okay, so if there are no further questions, thank you again, Sanghasri.
Thank you very much. Okay, I should be stopping it. Possible. Yeah.
Okay, thank you.
Okay. Thank you. Thank you very much. Thank you.
Thank you. Our next speaker is Mr. Harvansh Dandelia.